Hey, welcome back to Gabversity, where facts don't care about your feelings. It is an absolute pleasure, as always, to see all of you. Now, what we are going to do is we are going to construct what they call, I forgot what it's called. Oh yeah, that's right, spherical harmonic. A spherical harmonic. Hey, Dr. Dave. I believe everything's made it to the US. I believe they should be posted out either today or tomorrow from the US in Florida all the way to you guys. Hey. So the normalized angular wave function. Okay, and if you guys remember, when you drop a rock in a water and then the wave just blasts out in all directions as a sphere, it's an expanding sphere, right? That's on the top of a pool, right? When you drop the rock in of a pond, the wave is like circles, but actually it's three-dimensional, right? It's if in the quantum world it's three-dimensional, so it's pulsating spheres that radiate outwards. And it's called an angular wave function. But when you normalize it, when you normalize the wave function, you get something called a spherical harmonic. And we did the maths yesterday on how to actually create that equation. But now what we're going to do is we're going to construct one spherical harmonic out of the hundreds of millions of billions that possibly exist that create these different quantum particles that exist, right? We're going to create one of them. And it's actually going to take a few pages of mathematics to do. And step by step, we will expand it until we end up getting the actual equation of the sphere. All right. And this will be a snapshot in time. That's why it's only 3D, because you know that these waves are actually four-dimensional. But we're going to take a snapshot in an instant, and it'll give us a three-dimensional object. Okay, let's do it. So which one are we going to construct? We are going to construct this one here. It's called Y 1, 2. Okay, so this one here is called the magnetic quantum number. Okay, magnetic quantum number. And this one, this one is called the azimuthal quantum number. Okay, and there are heaps of these, right? So this is Y1, 2. All right, so now what we're going to do is start unpacking this whole equation. Now, Y1, 2 happens to be this. It's going to fill this equation. Y, there's the magnetic quantum number, and here is the azimuthal quantum number. And the general equation for this, for both angles, okay, that's theta, and that's phi. Okay, and remember that this wave is a 3D wave, and you can imagine a donut, right? A donut has a two-dimensional angle to make a three-dimensional object, because you've got the equator, or you've got the latitudes of the sphere, latitudes, and the longitudes, and when you combine them, it makes a sphere, and that's what's happening here. And it equals, okay, it equals this number here, okay, which is this number here. Okay, we've done this before. This number is based on m. So if m is 1, this will be -1. If m is 2, it's 1. If m is 3, it's -1. So it oscillates between negative and positive, right? And then we've got the square root of this big thing, which is 2l plus, should be a 1 from memory. Yep, 2l plus 1. Okay, and L is that number down here, which is the azimuthal quantum number, okay, over 4 pi multiplied by L minus the absolute value of m factorial, okay? And if anyone knows what factorial is, it's like, for example, 3 factorial equals 3 times 2 times 1. And 4 factorial equals 4 times 3 times 2 times 1. This actually appears a lot in nature, this type of number. Okay, now that is over L plus absolute value of m factorial multiplied by e to the I, and you remember I is the two-dimensional number, okay? multiplied by m, and that's m is the magnetic quantum number, okay? Phi, which is the angle, it's called the azimuthal angle, okay? And then it is multiplied by this magic function p, m, l, okay, of cos theta. So this is what y is. If we have one y, one of 2, then that means that we put it into this equation. And the m is 1 and the l is 2. Magnetic number 1 and azimuthal number 2. Which means that we put a number 1 in here, because that's a 1. And in the m we put the number, sorry, 1 is the m. I just stuffed that up because the l is a 2. See, I make mistakes all the time. So 2 by 2 is 4. L Brooks, hello, my dear. 2 by 2 is 4. Plus 1 is 5, right? Because this is for this one. 1, 2. So you put the 2 in there. So 2 by 2 is 4. Here, that's 2 minus, and that's 1. So 2 minus 1 is 1. And 2 plus 1 is 3. So that's 1 over 3. And that's 3 factorial. Remember, 3 factorial is 3 by 2 by 1. So that's going to be 6. Because 3 times 2 is 6 times 1 is 6. Here you go. E to the I and m, remember m in this case is 1, right, for this one. And then here, this is going to be p, right, this is called the Lagrange Polynomial, which we did yesterday, and we'll do it again today. 1, 2 cos theta, all right? So that's what's going to happen to that. But here is the next step. There's no point in putting all that in yet, because we need to know what the hell this thing is. And that, right, has this equation. Ciao. Oh, it's another bot. Damn these bots. What's going on? We're having a bot fest. Okay. That is right there. And remember, it's ps1, 2. So 1, 2 of x, by definition, is 1 minus x to the power of l. And l in this case is 2. Because if you remember, there it is, 1 and 2. Okay. And then m is 1. So that's going to be to the power of a half. So square root. And then that's 1, so the first derivative. If that was a 2, it would be the second derivative, third derivative, fourth. So it's a 1, so it's a first derivative of p l x. So p l, and we know that l is 2. So let's write that one out, okay? Now, so far, this still is not going to make sense because we're unpacking this slowly. Excuse me. Okay, so let's write this one out. So p, okay, of 1, 2 is going to equal 1 minus x squared outside of 1 over 2 multiplied by the first derivative of p2 of x. Okay, so now we have that which fits into here. Okay, and the cos theta is going to go into here. All right, but now we have another problem. What the hell is p2 of x? Well, here's the equation for the Lagrange polynomial. P of 2 of x is going to equal 1 over 2 to the power of l, which is in this case 2, times l factorial, which is 2 factorial, and then there's a 2 there, so the second derivative of x squared minus 1 all squared. Okay, and I'll show you once what that is. That's p2 is going to equal 1 over 2 squared times 2 factorial, okay, and 2 factorial is just 2 times 1, okay, and then multiplied by the second derivative of x squared minus 1 all squared. So there it is. So now we have everything to make up this whole equation, right? Because we didn't know what this was, but we figured that out. That's here. And then that has this in it, which is that. So it's a massive equation, right? Now, what we want to do is actually expand this, right? So first we're going to expand this one. So that, which therefore p2 is going to equal, well, 2 squared is 4 by 2 is 8, so 1 over 8. And the second derivative of this is the same as the first derivative of the derivative, which is 4x outside of x squared minus 1. Okay, which equals 1 over 8, and then the derivative of that is going to be 4 x squared minus 1 plus 8x squared. Okay, so then we put that, this thing goes into this, right? But we want the derivative of that. So now we have to get the derivative of this. Okay, so that implies that the derivative of P2 equals the derivative of this. So the derivative of this is what? It's going to be 8x plus 16x. What's 8x plus 16x? 24. And then 1 over 8 of 24 is 3. So it's going to be 3x, which equals 3x. All right, fingers crossed. I think I might have made a mistake somewhere. Let's just check if I made a mistake. Did I make a mistake? That is 8x plus 16x. No, I think I got it right. Yeah, I'm pretty sure I got that right. Yeah, I did. I did get that right. So, let's turn the page. And what we're going to do now is we're going to put that 3x into here. Okay? So this implies that P12 equals, and we figured out that this equals 3x. Okay? This whole thing is 3x multiplied by that. So that is going to be 3x by this, which is 3x outside of 1 minus x squared to the half. Okay, but now we can put this into here. And this is a function. So now we know that that's the function here, and it's of cos theta, which means we put cos theta where x is. Okay, so let me just block all this out. So therefore, P12 of cos theta equals 3 cos theta 1 minus cos squared theta, because we're just putting it in here, right, to the power of a half. We'll have a look at this. What's 1 minus cos squared theta? If you know your trigonometry or your trigonometric functions, you know that cos squared theta plus sine squared theta equals 1, which means that 1 minus cos squared theta is just going to be what? Sine squared theta. Well, if this equals sine squared theta and it's the square root of sine squared theta, then square root of something squared is just the thing. So sine theta. So therefore, P12 equals 3 cos theta sine theta. So all we've done now is we've unpacked this whole thing to figure out what it was, and now we can put it back into this equation. Okay. Thank you very much, Captain Deltron. Bose and Deltron, my favorite Gabversity students. Okay, so therefore, now we know that y12, okay, right, of theta and phi is going to equal, and we know that m is 1, which means that the e, that we did up here, if this decides to get into focus, you can do it. Come on, there we go. That little number here is going to be minus 1. Okay, so minus 1. Folk music, welcome back. Okay, I finally reached the bottom of the class. Bose. I think you earned yourself some fans, my friend, on Gabsmacked with your excellent support of Cassie. You know, therefore is 3 dots. Haven't seen many use that. Oh, yeah. Yeah, it's an old school one. Bon nuit. Sleep well. All right. So 2L plus L. Oh, sorry, 2L plus 1. 2L plus 1. Well, L is 2. So 2 times L, right? If you look up here, 2L plus 1. Actually, let me put it up here for you. I'll try and flip it across. Be right back. Keep up the magic. I owe it all to you guys, my friends. Sorry. This is got to get some sort of tripod. All right. So we saw here that 2L plus 1. Well, L is 2, right? For this particular spherical wave that we're looking at. So that means that 2 times 2 is 4 plus 1 is 5. So that's just going to be 5 over 4 pi multiplied by L minus the absolute value of m. So 2 minus 1 is just going to be 1, and 2 plus 1 is 3, but 3 factorial, 3 times 2 times 1 is 6. So that's going to be times 1 over 6. There it is. And then the next part, e to the I, m is 1, so it's just I phi with my little I, and we saw that this part, right, the p 1, 2 cos theta equals, we worked it out to be 3 cos theta sine theta. 3 cos theta sine theta. So there is the whole equation. I made that a bit too long, got over ambitious. And that's it. There is the equation now so far. We've now expanded it. So now we just have to simplify it. And that is going to equal, if it decides to frickin' unfocus itself, 3, so minus 3, right, outside, 5 over 24 pi e to the I phi cos theta sine theta. There it is. We're done. Okay, so that's the first part. That's a lot of pi. Yeah, that is a lot, mate. You would, RTMA would be proud if you could finish that. Okay, so now what we want to do is we want to check that it's normalized. Now, if you guys remember what normalized means in quantum mechanics, normalized means that when the probability of finding the particle in that whole wave function is 1. In other words, it's there. It's 100% there somewhere. Okay, and that's what being normalized means. So that means if this wave function that we've just created, if it's normalized, right? If it's true that it's normalized, then if we integrate it, and we integrate it according to the spherical rule on how to integrate a spherical function, then the answer should be 1. If the answer is 1, that means that it's true that the particle exists somewhere in that wave function. Right? There's a 100% chance you're going to find it somewhere in that state, that wave state. So now we have to integrate the bastard. And that's going to take even more maths than what we just did. All right, the first part that we just did was the easy part. Now we're going to have to do some triple integration. All right, so let's do it. Now we have to remember that the rule is, oops, if you guys remember, sorry, I just dropped my watch. Is everyone still with us here? I hope so. Right? If you guys remember that to normalize something, we said the integral of the wave function, absolute value or modulus squared dx, that was 1 dimension, equals 1. That was in 1 dimension. Okay? Now, in 3 dimensions, right? If you remember, we have to do dx, dy, and dz, but this is spherical coordinates. It's very artistic, eh? Yeah, that's true. With spherical coordinates, we only need 2 angles. So here's an interesting phenomenon. To make 3 dimensions with normal geometry, right, with Cartesian coordinates, which is like, you know, length, breadth, and width, right? Length, depth, and breadth, or whatever it is, right? You need 3 dimensions to make 3 dimensions. But with angular coordinates, so when you're using angles, to make something 3D, you only need 2 angles. So 2 dimensions in angular coordinates makes 3D. And if you think about it, it's like the Earth, right? With the Earth, all you need is the equator and like the longitude and the latitude and the radius. The radius would be within that, that's right. So the radius would be, you'd have the equator and the radius goes into the center, right? And then you have the longitude and the radius also goes up to that as well. So the radius is from in the center and makes the 3D. But that's all you need. You only need 2 angles. Okay, that means that we only have to integrate twice, not 3 times. So I'll show you what I mean. Okay, in 3D, but using spherical coordinates, we have a double integral. So we have the integral from 0 to 2 pi and the integral from 0 to pi. Okay, and we have the y equation we just made, squared, sine, oh, it's blurry again. Come back. Come on. Okay, sine theta d theta d phi. All right, so what we do is we integrate this inside bit first. And after we integrate that, then we'll integrate the outside with respect to phi. Okay, so we integrate inside and then we go out. This is multivariable calculus, right? And this becomes quite interesting because we already figured that out. This is up here. Okay, and if you guys remember, right, this squared, and this was ages ago, right? This squared, I'm going to show you what it is squared. I'll show you. Okay. Okay. The modulus squared, okay? The modulus squared, okay, equals the mirror image in the parallel universe of that sphere multiplied by the original. Okay? And now I watch you. That is too funny. Folk music. It's weird how life does that, huh? Alright, so now let's have a look. We see that we have minus, which equals minus 3, right? 5 over 24 pi. You thought that was a lot of pi, Captain Deltron. It's going to be squared. It's even more pi. All right, half, okay, e to the I phi cos theta sine theta multiplied by, okay, so this here is the actual function, and now I'm going to do this function, which is the mirror image in the parallel universe, right? Multiplied by minus 3, 5 over 24 pi to the half, e to the minus I phi, okay, that's the mirror image, my friends, cos theta sine theta. All right, so now we multiply them together. Well, minus 3 by minus 3 is 9, and 5 over 24 pi square rooted multiplied by itself, pi and by everyone's sleep calls. My friend, you sleep well, all the best. Obviously, that's a square root, so if you times it by itself, then you just get rid of the square root, it becomes itself. So 9 by 5 is 45 over 24 pi. Okay, so that's going to be 45 over 24 pi. Okay, now e to the I theta multiplied by its mirror image actually cancel each other out, because e to the I theta multiplied by e to the minus I theta, right, is the same as e to the I theta minus I theta, and that will become e to the 0, which is just 1. So that disappears every time. I've done that in past lectures. Cos theta sine theta by cos theta sine theta is just cos squared theta sine squared theta. Cos squared theta sine squared theta. Okay, so there it is. That is it. So therefore, the integral, the double integral from 0 to 2 pi, 0 to pi, of this harmonic sphere, or this spherical harmonic, modulus squared sine theta d phi, actually equals 45 over 24 pi, which will simplify. That simplifies to 15 over 8 pi. Ooh, there's a motorbike here. It's a street triple. That is, no, it's a Daytona. Yeah, that's my brother. All right, so outside the double integral, 0 to 2 pi and 0 to pi, all right, of cos squared theta sine cubed theta d theta d phi. There it is. So now all we have to do is integrate this to see whether we get 1. So now on the next page we will integrate this. Now how do we do it? Well, if you guys remember, cos squared theta is the same as 1 minus sine squared theta. Okay, so have a look. 1 minus sine squared theta by sine cubed theta is the same as sine cubed theta minus sine to the 5 theta. Okay, so then that equals 15 over 8 pi, just simplifying. Okay, 0 to 2 pi, 0 to pi of sine cubed theta minus sine 5 theta d phi. All right. So all we have to do now is integrate this and integrate this. All right. So that is now going to be the interesting part. Now we're going to get into integration. So just to recap for everyone, what are we doing? What are we doing? We constructed the spherical harmonic, which is, by definition, a normalized 3D wave function, which is a snapshot of the 4D wave function. We took a photo. So in real life, when you take a photo, you get a 2D image. But with these ones, it's actually an image of a 4D image. So it becomes 3D. And we created the wave function. And now we have to integrate it using the normalization method, which is integrating it. You get the modulus, you square it, multiply it by sine theta, and you integrate that over the double integral, which is over both angles, and you should get 1. Then that you know it's normalized. Now the reason we want to know it's normalized, to remind everyone, is to show that the chance of finding the quantum particle in that wave function is 100%, and 1 means 100%, 1 out of 1. All right, that's what we're doing now. So all we're doing is just basic integration now. Okay. So how do we integrate this mother effer? Well, I will show you how we integrate this mother effer. Okay. So sine cubed x. Let's do it. First, we're going to integrate theta. All right, we're going to integrate this. All right, what is the integral of this? Okay, let's just, d theta. So all I've done is taken it out of that big equation. So I've just taken this out by itself with respect to theta, the inside integral, right? That's all I'm doing at the moment, so that we can make everything simpler. Sine cubed theta equals, okay, integral of 0 to pi of sine squared theta sine theta d theta. That's just algebra now, right? Sine squared theta sine theta d theta. It's just algebra, because by that is sine cubed, obviously, right? So I've just separated that. Now, what does that do? Well, that makes it this. This is pretty creative that they, once you do a maths degree, they teach you how to do these things. Pretty damn amazing that someone came up with this. Sine squared theta is 1 minus cos squared theta sine theta d theta. All right. So I've just rearranged this. Now, why have I done this? Well, have a look at this. Imagine if I let u equal cos theta. Let u equal cos theta. Well, that implies that du equals negative sine theta d theta. All right. That's just a basic derivative. Now that's pretty amazing, because look at this. Sine theta d theta, okay? Well, look, it's right there, sine theta d theta. So now I can actually chuck in, which implies that minus du equals sine theta d theta. I've just put the minus on that side, okay? So that implies, right, that this integral equals, okay, the integral of, and I've got to change these, but I'll change that in a sec. 1 minus u squared, okay, minus 1 plus u squared, because it's a minus, du, okay, and also 0, cos of 0 is 1, so that's going to be 1 down the bottom, because that's 0, and if you remember, it's we put 0 in here, and we get that cos of 0 is 1, so u has to equal 1 when theta equals 0. And pi, okay, pi in here, cos of pi makes u minus 1, so it's 1 to minus 1 of this. All right, so all I've done now is convert this through substitution into this, which is, I find, freaking amazing, right? And that's going to equal, well, the integral of minus 1 is just minus u. So minus u, minus me? No, u. Haha, hilarious. And the integral of u squared is 2 over 3 u cubed. Okay? From 1 to minus 1. And minus 1 in here. So that's going to equal minus minus 1, which is 1. And then minus 2 over 3 minus 1 plus 2 over 3. Okay? And that is going to be 1 minus, that's 2 minus 4 over 3, which equals 2 over 3. There it is. Done. All right. I think that's right. So the integral is 2 over 3. I really hope I got that right. Let me just check if I've done that right. E equals big dicks in my ass. You know, every time someone appears, I never know if it's going to be that one guy that is always doing the big dick thing. It is so funny. Yeah, just too funny. Oh, man. Anyway, I think I'm going to stop the lecture here, right? And I may or may not do the rest. But ultimately, the answer is 1, because I've done it before and I've proven it's 1. But it's the same process. You just do the sine to the 5th, you integrate that, and then you chuck it back into this equation in here. So you integrate that, and then once you multiply it by this, you're going to get 1. What are these equations for, my friend? They are to get big dicks. So, always a pleasure to have you guys at Gabversity, where facts care not about your feelings. And it is crazy what is going on. All right. We'll talk to you all next time. By the way, I got my ethics assignment back based upon all the last lectures I did on ethics, and I got a high distinction. So I owe it to my discussions with you guys. All the best.